Okay. So photo price rearrangement. So similar to the thermal rearrangement, photo price rearrangements converts phenolic ester into ortho and para hydroxy aromatic alcohol. Okay. Yes. It's an aromatic alcohol, not the ketone. So in place of ketone, you can write the alcohol. So here, more particularly, you can consider it as a acetoxybenzene. So that means acetoxybenzene is converted into ortho or para acylated phenols. This is called photo price rearrangement. So not only the esters, enol also converted into undergoes photo price rearrangement. So let's take an example that is called acetoxy. If R is equal to CH3, acetoxybenzene on irradiation, that means it's a photochemical condition. Thermally, it's called as a Claisen rearrangement. In photochemically, it is photophase rearrangement. Obtained ones are orthoacetyl or para-acetyl phenols are the products. Then, if you are looking at the mechanism, acetoxybenzene are irradiated at the lambda max of acetoxybenzene. A ground state one is converted into a singlet. Singlet one crosses the intersystem crossing, and obtained one was the triplet. So this triplet undergoes cleavage. What is the cleavage? Cleavage of alpha carbon. So you are considering that CO is the functional group means alpha cleavage. So obtained one alpha cleavage means here one radical, and then yes, here radical, and then the pi electron cleavage. That means here one radical, here one radical. That means there will be a new bond formation between the carbon-carbon bond, and later on there will be a new bond formation between the oxygen and carbon. That is how this product is obtained. And the end product is loss of hydrogen radical. That means this hydrogen radical loses and forming a product. The product is hydroxy acyl phenols. Otherwise, we can call it as a hydroxy ketones. Of course, we can retain this ketone because it is a ketone only. It's also a ketone. Okay, fine. So this is the mechanism as well as the reaction of photo price rearrangement. Acetoxybenzene on irradiation, it gives ortho or para hydroxy, para acyl phenols are the products. Let us take one more example in the next slide. Okay, so here not only the esters means acetoxybenzene, amides also undergo photo rearrangement, enols also undergo photo rearrangement. And also enyl esters, okay, enyl, vinyl, V-I-N-Y-L, vinyl ester, enol, and amides also undergo photo rearrangement. So here, amide on irradiation, it gives orthoacyl or para-acyl aniline compounds. So enols on irradiation, there will be a bond cleavage between the carbonyl carbon and the oxygen, and then there will be a new bond for pi bond cleavage, homolysis cleavage, forming a carbon-carbonyl bond, and then later on oxygen-carbon bond formation, and the obtained one is a enol. So acyl enol. Then this can be converted into keto-enol tautomerism. Enol can be converted into keto form. That's also possible. Then here I am taking vinyl. This group is called vinyl ester. Vinyl ester also undergoes photo rearrangement. Initially, there will be a alpha cleavage. We can call it as alpha only. This is carbonyl carbon, and this is alpha cleavage, forming a two radical. Later on, by electron homolysis, forming a new bond between this electron and this electron deficient carbon, and later on a CO bond formation. So that means the obtained one is a dicarbonyl compound. I will go to the next slide. In the next slide, I am taking Norrish type II reactions. Norrish type II cleavage, we can also call it as a photoelimination. This is similar to McLaughlin fragmentation. So Norrish type II reactions undergoes the compounds or carbonyl compounds containing gamma CH function. So what is gamma? You can consider that here alpha carbon is there, but there is no gamma carbon. That means this carbonyl compound does not undergo Norrish type. Alpha and beta is there. This also carbon does not undergo Norrish type II reaction. This also does not undergo Norrish type II reaction. Whereas this one, alpha, beta, gamma. So at the gamma position, hydrogen is there. So the condition for compound to undergo a Norrish type II reaction is it should contain gamma hydrogen. That means this will undergo gamma hydrogen. When it comes to here, alpha, beta, gamma. Gamma carbon is there, but there is no gamma hydrogen. That's the reason this also does not undergo Norrish type II reaction. And when it comes to here, alpha, beta, gamma. So, but here there is a two hydrogen. That means this might undergo Norrish type II reaction. So here there are no carbonyl group, but here there is a carbonyl group, alpha, beta, gamma. Here also hydrogen is there. So this might also undergo Norrish type II reaction. So in the next slide, I'm taking a general example. This is a general example, a carbonyl compound. Adjacent carbon is called alpha. This one is beta, and this is gamma. So gamma contains hydrogen, and this might undergo Norrish type II reaction when it is irradiated with the lambda max of the carbonyl compound. So the what is obtained? Obtained one will be the cleavage, alpha beta bond cleavage. Alpha beta bond cleavage means here one double bond, here double bond. That means enol and then alkene is obtained. In addition to these two products, cyclobutane product also obtained, cyclobutane derivative. This we will call it as a side product, and this also we will call it as a Young's rearrangement product. Then you know that enol can be converted into ketophore stabilization one. So that means enol is stabilized through ketoenol catabolism. So overall, you can remember that type II reactions means the carbonyl compounds having gamma hydrogen undergo Norrish type II reactions. So let's look into the what is McLaughlin, and also what are the characteristics of Norrish type II cleavages. So McLaughlin means it's McLaughlin definition. It's again it's a definition for since the McLaughlin definition is similar to the Norrish type II reaction, we can also take it as a definition for the Norrish type II reactions. Then transfer of gamma hydrogen. Transfer of gamma hydrogen to a carbonyl oxygen followed by homolysis. Homolysis means cleavage. So homolysis cleavage of sigma bond. What it means? It means that gamma hydrogen is transferred to a carbonyl compound followed by homolysis of C alpha C beta bonding, and this type of reactions are called Norrish type II reactions. These are also called as photoelimination. The resulting products are enols and olefins. Enols maybe get stabilized in the form of keto form. The competitive side product is a cyclobutanol derivative. What are the characteristic Norrish type II reactions? Irradiation at absorption wavelength, that's lambda max of the carbonyl compound, is the one characteristic. Another one, type 2 reactions is possible in liquid state as well as the solution state. Cleavages, photocleavages occurs. The carbonyl compounds having only gamma CH function undergo Norrish type 2 cleavage. So excited states are, what are the excited states in Norrish type 2 reactions? N2 pi star singlet, N2 pi star triplet are the excited states, and N2 pi star singlet cleavages are stereospecific, N2 pi star triplets are the cleavages are the non-stereospecific. Then the reactive intermediates are 1,4 biradicals, and 1,4 biradical intermediates are stabilized by the following routes. The one route is reverting into a starting material, and the other one is the direct cyclization. This direct cyclization is also called as Young's cyclization products. Usually cyclobutanol are the product, and by undergoing C alpha, C beta homolysis, that is again this also a photo elimination. And here the products are enols and olefins. With this, I will go to the next slide. In the next slide, I'm taking example. What is the example here? A carbonyl compound and the gamma hydrogen containing one. So this undergoes, this on irradiation undergoes Norrish type II reaction. There will be a cleavage between the alpha and beta carbon. Here there is a cleavage. That's the reason here double bond and here double bond. Enol will be forming. Later on, enol will be converted into ketone. This is about the Norrish type II reaction and the products, alkene and enol. If we are looking at the mechanism, the ground state gamma hydrogen containing carbonyl compounds on irradiation use singlet carbonyl compound passes the intersystem crossing and forms a triplet one. In this triplet undergoes transition state. What is the transition state? Gamma hydrogen is obstructed. There will be a bond formation between the oxygen and the gamma hydrogen, and there will be a pi bond cleavage, and there will be a homolytic cleavage of alpha beta bond, carbon-carbon bond. So it forms a 6-member transition state. Why it is 6-member transition state? Here 2 electrons, this is 2 electron, and this is 2 electron. Totally there are 6 electrons are involved. So that's the reason it's a concerted reaction, and it is a Norrish type II reaction. The obtained products are enol and alkene. I will go to the next slide. In the next slide, I am taking one more example. This is also a Norrish type II rearrangement. And here we are explaining how the cyclobutanol is obtained. So that means there will be a new bond formation between this radical and this radical, this radical and this radical. Then there is a formation of cyclobutanol. Suppose the hydrogen radical is shifted from here to here, then a ketone. That means this is a reverting the starting material, going back to the starting material. So going back to the starting material, formation of cyclobutanol, and then formation of enol and ene. These are the 3 products of Norrish type II reactions. So here I'm taking an evidence for the gamma CH participation in the Norrish type II cleavage. So what is that evidence? This is the general reaction. This is the evidence reaction. What it means, if the gamma hydrogens are replaced with deuterium, then this Norrish type II reaction is carried out. ene and enol are the product. What is the difference between the deuterated and non-deuterated one? So deuterated one rate of reaction is slow compared to the non-deuterated one. This indicates that uh, gamma CH are participating in the reaction. So you can say that the replacement of the gamma CH with heavier isotope decrease the rate of Norrish type II cleavages, and this will be the evidence for the gamma CH participation. Then evidence for the reversibility of the 1,4 biradical intermediate. That means in place of gamma CH, if okay, if this reaction is carried out in methanol, more particularly deuterated methanol, then it is observed that at alpha position, deuterium is obtained. This indicates that uh, reversible reaction of Norrish type II reactions. So here is the mechanism. What is that mechanism? Gamma CH obstruction forming a OH bond. And again, if there is a OH bond cleaves, then it's nothing but a starting material. You are going back reversible. And when it is going back, the deuterium will form a bond here. So that's the reason gamma position deuterium is there. And here, it's again a reversible reaction. So you can remember that if the reaction, okay, what is that reaction? Norrish type II reactions are carried out in presence of deuterated methanol. It is observed that deuterium is fixed at the gamma position. This indicates that reversible nature of the 1,4 diving, 1,4 Norrish type II reactions. With this, I will go to the next slide. Here I am taking a particular example. What is that particular example? S plus methyl 2-heptane. This is the S plus methyl 2-heptane. That means here C is there, CH3 and C2H5, and then CH2, and then CO, and then CH3. So totally 5 carbon atom plus is there, dextrorotatory one. The dextrorotatory related to this chiral carbon. So when this is irradiated with the lambda max of methyl 2-heptane, it is observed that the obtained is this is the singlet one and this is the triplet one. So singlet means opposite electrons and triplet means same side or parallel electron. So then you know that there is a conversion of pyramidal carbon into a planar carbon. So because of the pyramidal inversion and electron spin inversion, the obtained products are the racemic mixture. At the same time, Young's rearrangement reaction. Young's rearrangement reaction means cyclobutanol is the product. How the cyclobutanol is the product form? Because the electron spins are in opposite direction, so there will be a bond formation between this carbon and this carbon. So overall, you can observe that when you are taking an example of S plus methyl 2-heptane, the ground state one will go to a singlet one will go to a triplet one. So then this is the singlet structure, this is the triplet structure, and in the triplet structure, it is observed that there is a pyramidal inversion. That's the reason it is observed a racemic mixture is obtained. And the Norrish type II products are enol and ene are the products. So this is only in the next slide also, this is only continued. Okay, right. Then this is the next slide. So here explanation for the cyclobutanol formation. you know that alpha, beta, gamma, okay, and then alpha beta bond is cleaved, and there is a if there is a bond is cleaved means here there is a double bond. Enol is the work time, and then in addition to that, the cyclobutanol is also a formed. Then this enol formation is the Norrish type II reaction, and cyclobutanol derivative is the Young's uh, rearrangement reaction. But if we are looking at the this young cyclobutanol product formation depends on the substituents, of R and R dash. Suppose R and R dash are the hydrogen, then Norrish type II reaction will be 71%, cyclobutanol will be 29%. If R and R dash is equal to CH3, that means bulkier. In such case, Norrish type II reaction is 11% and cyclobutanol will be 89%. Overall, you can look into that. Look at the substituent present at the alpha position of the carbonyl group. If the bulky groups are other than hydrogen, then cyclobutanol will be the major product. I will go to the next slide. In the next slide, I am taking explanation. This explanation is here. This is the continuation of the previous slide. So here it is shown that how the spin inversion takes place. Okay, then this also a continuation, and this is here I am taking an example, more particularly alpha substituted cyclohexanol. This carbon is alpha, beta, gamma. So gamma hydrogen obstruction, and then alpha beta bond cleavage. So these two are the products of Norrish type II reaction, and the enol one is converted into ketone. Similarly, in this one, there is a possibility of the two gamma hydrogen. This is one gamma hydrogen. This is another gamma hydrogen, and this one will be the alpha beta cleavage. So then the obtained one is this intermediate. This enol can be converted into ketone. So in this one, taking this is one gamma hydrogen, this is another gamma hydrogen. So in this one, here there is an alpha beta breakage. That's how this product is obtained. I will go to the next slide. Here I am taking few more examples of Norrish type II reactions. This is the cyclobutanol. In this cyclobutanol, this is again gamma hydrogen, then gamma hydrogen obstruction, and then here you know that alpha position CH3 is there. Since the alpha position bulkier group is there, this undergo cyclization, forming a Young's rearrangement product. And here also Norrish type I reaction. Type I cleavage means alpha cleavage. This cleavage, alpha cleavage is Norrish type I reaction. So alkene and aldehyde are the product. I will go to the next slide. In this slide, here I am taking a cyclohexyl phenyl ketone, phenyl cyclohexyl ketone. In this one, alpha, beta, gamma. Here there is a hydrogen. Then this hydrogen is obstructed, forming a enol, en and r. So this enol is tautomerized to ketone. Similarly, this one here also same. Both are identical one, but only thing this is the axial one, and this will be the equatorial. In both the case, axial one type II reaction, axial equatorial one will be the type I reaction. So this is again equatorial one. In the equatorial one, what is happening here? Norrish type II reactions. In the Norrish type II reactions, alpha alpha beta bond cleavage and forming a enol product. So enol product. Then the obtained products are ketone. I will go to the next slide. In the next slide, I'm taking few more examples. So here, alpha, beta, gamma. And similarly, alpha, beta, gamma. So two things are possible. And this bridged hydrogen, and this is again axial hydrogen. So here, bridged hydrogen is near to this carbonyl oxygen. So this is cleaved, forming an intermediate like this. Enol is like this, and this is enol is nothing but a cyclopentyl ketone. Similarly, here I am taking one more one, alpha, beta, gamma. This hydrogen is cleaved, and this is the product. I will take one more example. This is also here also you should be able to identify the substitution, alpha substitution. Here alpha, this is the alpha substitution. Alpha substitution CH3 is there, bulky one. So it makes a cyclobutanol of the product. So here alpha, there is no substitution. So hydrogen obstruction forming a enol one. Enol undergoes keto-enol tautomerism forming a product. Suppose if you are taking a product, ketone substitute, cyclohexyl substitution at the alpha position. So that means this is again a bulky one. Since it is a bulky substitution at the alpha position, undergoes cyclobutanol derivative as the major product. This is the one will be the major product. Otherwise, if there is a cleavage at Norrish type II means these two are the product. Since there is a alpha position bulky group, this CH2, CH3, if we are considering this bulky group, then this will be the product. I will take one more example. So here alpha, beta, and then gamma. This is the gamma. That means here hydrogen obstruction forming. These are the three products of two products of, okay, this is one more. Two products of Norrish type II reaction. This is again one more identical one. I will go to the next slide. In this slide, a cyclopropyl group, more particularly a carbonyl carbon one, alpha position, beta position, and gamma position. So gamma position, hydrogen obstruction. On irradiation, it will give you the Norrish type II reactions. What are the Norrish type II reaction? In ketone, in all initially, later on, in ketone are the products. And you can observe that this is alpha. So in this one, beta, gamma. So obstruction on this one and forming a cyclobutanol is the Young's rearrangement product, means side product. In addition to that, this is also a forum. So rearranged product, a six-membered alcohol also forum. You can write the mechanism, how six-membered alcohol is type. Then again here a carbonyl compound, alpha, beta, gamma. So at the gamma position, CH3 is there, and alpha position there is no CH3, and then cyclization forming this product. Okay, like this we can look into the several examples with respect to Norrish type II reaction. This is again one more example, a gamma obstruct. So this is how a radical 1,4 carbon radical cyclobutane ring formation. If there is a bond formed between these two carbon means cyclobutane ring formation. And suppose if there is a pi bond cleavage and there is a bond formation here and there is a cyclization from this carbon to this carbon, then this is the product is obtained. That means for your previous question, here is the answer how six-membered alcohol is obtained, how four-membered alcohol is obtained. I will go to the next slide. In the next slide, I'm taking two more examples. You can observe that here two ketones are there. So this is the, you are considering that this is a carbonyl compound, alpha position. That means here alpha position does not contain CH2. And of course, gamma is contain CH2. That's the reason this will undergo Young's cyclization, forming cyclobutanone. Cyclobutanone will be the product. Similarly for this one. So this also undergo Young's cyclization, forming a cyclobutanol derivative. So, and here, what is this? It's an keto ester. Keto is, this is a keto, and this is the ether. Keto ether. Suppose keto ether means alpha, beta, gamma. So gamma position hydrogen is there, alpha also hydrogen is there, and alpha it undergo cyclobutanol derivative. Ones are the product. So what we observed up to this, we are checked about the gamma hydrogen and alpha hydrogen. Here, alpha hydrogen is there, but there is a gamma hydrogen. And then this undergo alpha beta cleavage means it is possible to get carboxylic acid and alkene. Similarly, suppose a ester, this is the ester. Okay, one more example of this kind, alpha beta cleavage, gamma obstruction forming an acid and alkene. One more example, this is again alpha beta gamma. Gamma hydrogen is there, so it undergo Norrish type II reactions and cleavage between the alpha and beta, forming a acid and alkene are the products. I will go to the next slide. In the next slide, I am taking two more examples. So you can observe that here two gamma CH are there. So if there is a two gamma CH, the weaker gamma CH1 preferentially participates in the Norrish type II cleavage. So from these two, you have to identify which one is weaker. So here, this is CH2, CH31, whereas this one is CH21. You know that CH2 will be the weaker compared to the CH3. That's the reason hydrogen obstruction occurs at this carbon, not at this carbon. So the obtained products are a ketone and alkene. So here I am taking one question. You can answer for that. What is the question? If 3-methyl pentanol, so if 3-methyl pentanol underwent Norrish type II cleavage, show the products. This is the 3-methyl pentanol. This is the 3 position and this is the 1 position, 3-methyl pentanol. Here you have to identify the gamma hydrogen, alpha, beta, gamma. This is one gamma, this is another gamma. But again, you can observe that this is not the weaker gamma hydrogen because it is a primary carbon. This is the weaker gamma hydrogen because it's a secondary hydrogen. That means there is a cleavage on, means obstruction of hydrogen radical occurs at this carbon, not at this carbon. And there will be a cleavage between the alpha and beta carbon. The obtained products are alkene and acetaldehyde. So let's take one more example, photo decarboxylation. That means in presence of light, a decarboxylation occurs. Let's take an example, keto acid. So pyruvate, this also call it as a pyruvic acid. So pyruvic acid on irradiation with the lambda max of the pyruvic acid, it is observed that decarboxylated, removal of carbon dioxide. Then what will happen? The obtained one is the acetaldehyde. Same as similar to your living means beta decarboxylations, ketoester decarboxylations. Then here I am taking one more example. What is that? Naphthyl. This group is called naphthyl, and this group is called acetic acid. Naphthyl acetic acid undergoes photo decarboxylation in presence of light, forming a 1-methyl naphthalene as the product. In the next slide, I am taking mechanism for the photo decarboxylation. What is that mechanism? Initially, there will be a loss of means alpha. This position is substituent, and to this substituent, this is the half. And otherwise, what we can say that alpha, beta, gamma. So at the gamma position, the pi electron undergoes homolysis, and then the acid OH undergoes homolysis, so forming a CH bond at the first position, and there is a radical on the E carbon, and then later on decarboxylation. That means homolytic cleavage of the carbon alpha beta 1. Then the obtained one is a T intermediate. Carbon dioxide is going, this part is going, and then this is about to form a double bond, and then there is a loss of hydrogen radical, and not the loss, movement, 1,3 hydrogen shift. This hydrogen radical is shift from here to here, so forming a 1-methyl naphthalene as the product. So then I will go to the next slide. In the next slide, I am taking the photochemistry of alpha beta unsaturated carbonyl compound. So here, photochemistry of alpha beta unsaturated carbonyl compound means these are the carbonyl compound contains a double bond at the alpha beta position. So alpha beta unsaturated carbonyl compounds undergo following photochemical reactions: photocyclodimerization, photocyclo-addition reaction, and pi bond migration, and cis strands are geometrical isomerism. So that means photochemistry of alpha beta unsaturated carbonyl compounds undergo photocyclodimerization, photocyclo-addition, pi bond migration, cis strands, and geometrical isomerism. So let's take the first one, the photocyclodimerization. So cyclic alpha beta unsaturated carbonyl compounds undergo photocyclodimerization. So here I am taking an example. You can observe that I am taking the two example. One is a 5-membered alpha beta unsaturated ketone. Another one is a 6-membered alpha beta unsaturated one. Between these two, 6-membered one will be the stable compared to the 5-membered one because of the steric effect. Then you can also, let's take one more example. This is also a alpha beta unsaturated carbonyl compound. This is also a alpha beta unsaturated carbonyl compound. So that means here photocyclo addition. That means 2 plus 2 pi addition. So 2 pi electron cyclo addition means this will be the product. Suppose this pi bond, okay, undergoes 2 plus 2 addition with this pi bond, then this product will be the product. This is the trans one, and this is the cis one. And how this trans is formed? By the combination of these two pi bond and these two pi bond. How cis is obtained? This 2 pi bond and this 2 pi bond one will give you the cis one. Let's take one more example. So here 2 plus 2 cyclo addition, 2 pi electron, cyclo addition. But here you can observe that there is a difference. What is that difference? This 2 plus 2 addition is called head-to-head cyclization, head-to-head cyclization. And this one will be the head-to-tail